So hopefully you get a couple of things out of my talk. I want to get started with what do I mean with distributed architectures. What you see here is a rather small distributed architecture. It actually shows, I think, a little blurry though on the screen, but what it shows here is a smaller Kubernetes environment from one of our customers that use Dynatrace. It is 323 different nodes being monitored with all the dependencies between the nodes. And this is also pretty cool, I thought. It looks actually kind of interesting how we visualize the dependencies. The same Kubernetes cluster has 4,229 Kubernetes pods running a little more than that in containers and obviously hosting a lot of services. And you can see that distributed architectures can become bigger and bigger and bigger, and also a lot of connections. And when we talk about distributed architectures, we need to take all of these dependencies and how things talk with each other into consideration. So that's one thing that I want to give to you, that always be aware of all the different connections and dependencies between your services. Now, talking about performance, I actually need to pick the first guys in the second row here. When you think about performance, what is performance for you? Can you give me, what would you look at? What kind of metric?
Working application. Fast working application.
So fast is response time, right? Anything else, performance? The capacity to serve many connections. How would you, can you give me a metric, the capacity to serve many connections?
It's the ability to measure how many connections the system can withstand.
So like a throughput, like what's the throughput of a system? How many connections or requests can a system handle? Good one. I want to give you a different performance metric now. What you see here is a screenshot of one of our features that we built into our product. It is Aws Monitoring. So what we do with Dynatrace, we monitor hosts, applications, and services, and then we also pull in data from external data sources like AWS. In case you are familiar with AWS and monitoring, AWS provides the AWS CloudWatch API. That's also the one we are using. In the first iteration of our implementation, where we pull metrics back, in a rather small environment, we did a little performance analysis. And we figured out, in order to capture data and get more metrics from AWS for a rather small environment, 12 EC2 instances, 1 ELB, 1 RDS, you see it's rather small. It took us 907 API calls to AWS. It took a total of 41 seconds to query that data, and 97 different threads on our side were occupied by that. That was the first implementation. It was not our fault. The fault was that the Amazon API back then only had a single fetch query API available. Now we optimized that, or we worked with AWS. They then provided better bulk fetching APIs, and so we could immediately reduce the number of round trips. We also could optimize a little bit on our threads, and also the time was much better. The more important thing, though, to understand, and this is what I mean about performance, is also all the things you said earlier is correct, but performance is also how much does it cost us to run that system. Because even though an individual call to an API like AWS is very cheap, $0.01 per 1,000 calls, that's very cheap, but it really adds up. And if we can reduce the number of calls, it's not only faster, more efficient, it also costs less. So if your system make any calls to external services where you may have to pay for it in whatever form, look at the number of dependencies and the number of calls and how we can optimize that. Another thing we've learned over the years, when you start building distributed architectures, you are going to end up with architectures that are getting more and more complex, right? You're getting architectures where your dependencies grow because the big monoliths are getting broken into smaller pieces, and therefore you have more moving parts, and an individual smaller component can have a big blast radius. To give you an example, a single bad update to a service can impact multiple other services because of all these dependencies. I think this is something you need to understand if you build distributed systems. The smaller the components, the more you have, the more resilient you need to make the system around it in order to minimize the blast radius. So that's why what I want to talk about you today are 8 different, I would say, patterns that we have seen when we analyze distributed architectures. There are some in there that should be very basic, and hopefully all of you understand already. For those that are new in the software engineering world, hopefully there's also these basic ones are something that you learn, but then we're getting into more exciting use cases. The first one is the M+1 pattern. That should hopefully be, it's a very simple code. So very simple loop that is summing up a total quote of different products in an insurance application. Very simple loop, right? Works well within a single process. But the thing is, if you're, for instance, externalizing one of these calls into an external service, this can become a problem. And I'll show you, and this is actually from one of the customers that I've worked with here. I see there's the gray, there should be, let's see, there should, oh, here we go. There's a little gray, you can see, yeah, I make it like this. You see all the different bars. So these are all the communication streams. So what they did, they had a quote service, which used to be a Monolith, and they extracted the thing that I showed you earlier into a product service that ran distributed across, in this case, 3 different instances. Now, the single call to a quote ended up in a total of 44 calls to the product service. After they made the decision, well, let's just break the monolith apart, put it into individual services, because then we can scale the individual services much better. But you always have to think about what is the impact of it. In this case, a bulk API, like we saw earlier with the Amazon API, would make much more sense to avoid all these individual round trips. Next example is another online financial service, LandPay. They also run their architecture on a cloud platform. What you see here on the front end, incoming requests, a single incoming request turns into 74 database calls and 24 messages put into a queue. These 24 messages are then picked up by the individual listeners. All 24 messages go into these 3 listeners, or 24, 22, and then the remaining 2 go into the bottom ones, and then it goes on to the next layer, and then it goes on and on and on. So what you see here from left to right is an end-to-end transaction flow, or service flow as we call it, from a single transaction across multiple services that are talking with each other through queues. And there's nothing wrong with this, but I think what's wrong with it that you need to understand as an architect what it actually takes to get one single request through your distributed system. And as you start to build distributed systems, you really need to architecture the individual interfaces well and better to avoid a situation where completely kind of, touching too many systems in too many ways. Does this make sense? Quick question, yeah? Good. All right, you don't, for saying yes, you don't get tickets, unfortunately, but all right, what else do we have? The next thing is I just need to make this here a little, there's something obscuring my screen. Here we go. The next thing we have, and I think I do this again so that you can see the gray lines again. Same example as before, the query service, we saw the product service earlier, and now we focus on the database in the back. The same example, one call here ends up in 87 different database queries, because of every single time you call the product service, they also make multiple calls to the database. A lot of people are not looking into this, especially if you're responsible just for the quote service or just for the product service and you never look at the end-to-end architecture. So what I would like you to do, turn on your logs, turn on your metrics for your database access layer that you use, whatever you use. I'm sure they have some type of metrics to expose. Use monitoring tools, use tracing tools, and get an end-to-end understanding. Another example, one of my friends has built an e-commerce solution, and it was really cool a couple of years ago. They had very small customer base. And there was never a performance issue unless they started growing in the terms of the customers and in the number of products they had in their product catalog. So here's a single search. A single search on the product catalog made a cascading call to the database in the back end, totaling up to 26,000 different calls to make a single query to retrieve a product in the product catalog. Right? This doesn't look pretty. The thing is, you can detect these things, these n+1 query patterns, even with small data sets. You don't need large load tests. You don't need large data sets to understand and to see that you make the same call multiple times. If this happens in a single request end-to-end, it should ring the alarm bells. Payload flood, next kind of use case. So what you see here is again from a different monitoring tool and also what's called a transaction flow. These are always be read from request is coming in here, a document is being sent to a Java application server, is being sent to the first process, then to the next, then to the next, then to the next, until the whole thing is finished. What we did from an analysis perspective, we actually looked then how many bytes are sent back and forth, and hopefully you can read this. So this was a 30 megabyte document, I think a 20-something megabyte document, and it turns out when we analyzed a single document flow that the whole document was sent from one service to the next, to the next, to the next, even though each individual service just added or needed a little piece of the whole document. So, right, to give you kind of the overview, actually it was 10, there was 21 in the end. A 10 megabyte document was sent to the first doc processor, then turned into 18 megabyte, 20, 21, and there's a lot of data that has been sent back and forth between the internal networks. Now what they did, they reduced the total transfer size from 69 megabytes to 31 by breaking up the processing chain, loading the initial document, and then sending only those pieces to, let's say, the encryption, what does it say here? The transformer, the signer, and the shipment, and the initial doc processor. So breaking up the logic. This immediately saves more than 50% of network bandwidth. Okay, network is cheap, but it's not endlessly available, and especially if you're sending a lot of bytes between different data centers in the cloud, where sometimes, obviously, you have to pay for that too, right? Not only sometimes, but typically. Next thing, granularity. The same example from before. They then went a step, I think, too far ahead. So what you see here is another visualization of that flow. And they figured out that all of these 4 components needed this encryption module. That was a Java module, and they thought, well, it's a module, and if everybody needs it, we just externalize it, and so that every individual service can call it when it's needed. The problem now, for a single document that was processed, they ended up with 316 calls to that central service. That was completely overloaded, became the bottleneck, and also the additional network overhead didn't make sense at all. So hopefully by now it is clear that always look at the end-to-end request, transaction, whatever you want to call it. There's a lot of tracing tools out there. There's open source tracing, there's commercial tracing. There's a lot of people that build tracing themselves by using the logs, but please do it. Quick question, who is using any type of tracing technology right now? All right, so if the person next to you just raised the hand and you did not because you don't use it, then maybe you just say, hey, so what are you using? It's always good. And if you don't use anything, then you can always come back to my company. Tight coupling is the next use case. What you see here is another visualization. And by the way, as you hopefully see on the bottom, I will share the slides, obviously we will share. I always added links to either blog posts, to videos or to any other material that explain more about that actual story. Okay? In this case, breaking the monolith. So another interesting use case where breaking the monolith led to too-tight coupling. The previous one, so this used to be all in a single large monolith, and then the company decided to break it up. And what they did, they broke it up based on what they thought makes sense, based on how they thought the system works best, and they broke it up by, for instance, extracting the journey service into its own component, the booking service, the credit card, and what do we have here, the check destination. However, what it turned out when they then ran their first performance tests afterwards, there was a one-to-one correlation between the journey service and check destination, but they put them apart into completely different parts of the infrastructure. That means a lot of network going back and forth, even though it didn't make sense, because the only service that ever called check destination was journey service. So this is another example of don't extract it, doesn't make sense. Okay? All right. Next one, next use case, inefficient service flow. Here I always draw parallels to web performance optimization. Is anybody in here on the front end side maybe of the house and is familiar with web performance optimization? Yes, only one. Come on, there's more. I know it's late. Thank you. Again, I have to come up with these flows because the flows, these transaction flows, these traces tell us so much. This is a very simple flow of an app, and this is how it looked like after the first release, and everybody was kind of happy. And then they realized a couple of releases later, after they did not pay close attention to what the developers and the architects were actually doing, that the same application became much more complex because they had, as you can probably read for yourself, the n+1 query problem, so the same services calling each other multiple times, including new third-party service, recursive call chains. So there were a lot of services that were calling each other recursively, and therefore the whole flow became much more complex. This all can be avoided by constantly looking at what's going on end-to-end. Right? Another very classical view that I see a lot, the nice waterfalls of a trace where the same microservice is called multiple times in the back, and the same service calls the same database queries and then calls itself again and again and again. So this is another nice cascading waterfall effect that you see here when you don't do your work right. Good? All right. The next thing I want to talk about, and this is where I need to give credit to Adrian Hornsby. I had the pleasure of watching him on stage at a developer conference in Austria. That's where I'm originally from. He is also a developer advocate, and he talked about timeouts, retries, and backoff. In the slide notes, I also have the links to his blog post series. Quick question, so maybe because it's time to give out another ticket. What's the worst thing that can happen with timeouts? So what's the worst thing that happened to you with improper timeouts? No timeout, so infinite timeout. Yeah, that's a good one. Too small, that's a good one. Where too small? Where too small? In the front end, in the back end? Or in general, too small? So let's actually have a look at this. So this is what I took from Adrian. The example of a user calls an app and there's a backend database that is already under pressure. The front-end timeout, 10 seconds. The backend timeout, default, 60 seconds. A lot of frameworks use default timeouts for a good reason. There should be a default, but the defaults are never optimized for your environment. And especially the defaults can never be optimized for your environment because they don't know your end-to-end architecture. But too many timeouts are 60 seconds. So here's what happens. The database, what this symbol should show here, is already under pressure. That means assuming in a situation where the database is already slow, when the user makes a call to the app and they're executing an insert statement and that takes longer than 10 seconds, what happens? Retry, right? The front end retries will execute another insert, putting even more pressure on it, and therefore, eventually, like you just said, you're basically filling up all of your use connections. They're all busy with something that nobody needs anymore. Right? This is a bad thing. This should be basic for architects and for performance engineers, but I know that not everybody in the beginning raised their hands, so hopefully this is something new. How can we solve this problem? We solve this problem, first of all, by really investing time and figuring out what should be the perfect timeout. In this case, the timeout should obviously, in an ideal world, 10 seconds minus the time elapsed. So 10 seconds, because that's the timeout here, minus the kind of time elapsed between how long it takes to make that call from here to here. Now that's obviously, that takes time and performance engineering and monitoring to figure this out, but eventually you get there. But that's not the only thing we want to do. Because what happens now is if there is an insert, right, and it fails because it takes too long, we add an additional lag. We add what's called backoff. So instead of retrying after 10 seconds, we retry after 12. And if that doesn't work, then the client in the front retries after 4 seconds. And if that doesn't work, I guess you get the idea, we basically try later and later. Right? This is the idea. So we're waiting longer and longer, and this is what's called backoff strategy. You're backing off. It's like if you go to a bar and the bartender is already completely overloaded, it doesn't make him faster if you keep asking him for the next beer because he's already overloaded. Right? So just step back, wait a little bit, and then try it again. Hopefully this was a good example, but because I know we are all thirsty for beer. So the other thing that Adrian told me about this, while this is a great strategy, now there's different ways, whether you do linear backoff or exponential backoff, where you wait longer. Regardless of which backoff strategy you use, the problem is if you have a distributed system and one of the components is getting slower, like in my case, the database, and then all of the clients in the front have the same algorithm to wait longer and longer and longer, they will all hit the service again at the same time. And this is why there's a concept of adding jitter. That means don't do 2, 4, 6, 8, 16, 32 seconds, but add some randomness to it. Because otherwise, if I'm looking at the 3 guys here, right, if you all have the same strategy, then after 2 seconds you come back, after 4, after 8, and then you're completely overloading me again. That's why jitter means randomly distributing it. And there's different strategies for that as well. Good. All right. Next thing, dependencies. I think I talked about this already more than once, but this is another view of a beautiful application that starts somewhere here with the user, goes to the front end, and then there's a couple of backend services. But the big story, the real story here looks like this, right? This is also a rather complex system with a lot of dependencies. So the point here is you always, as an architect, need to look beyond the iceberg. And here's another example from a company that I recently worked with, Stepstone. I just saw them in Krakow because I was also at Devox this week, and they were also kind of having a booth there that reminded me to actually add this example in. Right? So what they have, and we were on stage together at a conference in Berlin, and you can see how already complex their system is. If you just look at the front end, if you believe, well, I'm just responsible for making the website nice, the front end, then there's a lot of things that can happen in the back. So always important. And my point that I also want to make when it comes to dependencies, it's not only important to look at the end-to-end, but if you are a developer and you're responsible for an individual service, then always ask for real production data or testing data that shows you who is actually calling you. Because if you write a service that becomes heavily used in an architecture, maybe when you start implementing that service, there's just one person or one other service using it. But then it becomes popular. Then you start using it and you start using it. So always keep an eye out who are your customers. Because as a service owner, you now have customers. And these customers are other services maybe in your organization. So you have to treat them well. You have to understand their requirements. You have to understand how they are using you. Because if you do, you can build better service improvements, like a bulk API, what I meant in the beginning with AWS. Or if you make a major change, you know who to inform about these major changes, and you know who you potentially impact. So, to recap what we have just gone through. Remember the n+1 call pattern. So if we make the same call multiple times, this is very easy to measure, even without a distributed tracing tool. If you're responsible for one service, you can log how often you call another service within the same context, within the same transaction context. And you can just log this out. n+1 query, same, it's basically the same thing than the number 1, but it goes to the database, because most of our systems, I would say all of our systems, depend on some type of data store in the back that we query. So that's why the n+1 query is also very important. By the way, which reminds me, I'm not sure if I actually explained why n+1, why we call it that way. Does anybody want to explain and win one more ticket?
Yeah, if we have a tree structure and we start with the first one, we want to collect all the data related to that, we end up with n+1. We started with the root and we ended up with the other dependent entities.
Mm-hmm. I have another example. If I have a product list, I have my first query that says, give me all the product IDs in that list, and then I go over in a loop and then query everyone individually. That's another one, but this is also good. That's why it's called n+1, or it should actually be called 1 + n, because you first make a query to figure out what's your record set. That's the first. And let's say a list of n comes back, and then in a loop, you go over everyone. That's why it's called the n+1. How can you detect it? Well, you can easily detect it if you see the same query with maybe different bind values multiple times in a single transaction. Remember payload flood, the granularity, I think they should all be, remember them. I also really stress timeouts, retries, and backoffs. Very important if you are architecting your distributed systems. Now, the last thing I want to leave you with is, this is all great, but I told you can write your own logs, and you can do this, and you can do this. I want to give you a little bit more idea on how we can automate all of this, because I don't want you to spend 15, 30 minutes, or even an hour per day to log something out and then always analyze it. This doesn't make sense, right? We live in an automated world. So I want to show you, and this is also what we built into our open source project, especially into the component that is called Pitometer. So you can use it, you can download it from GitHub. So what is this all about? It's really about automating the architectural validation or architectural regression analysis between different builds or configuration or deployment changes. You remember this one from earlier? If this is build 17 and this is build 21, then obviously somebody didn't have a close look at the changes between these 4 builds. Because we can, if we look at this data in an automated way, easily identify that I need to take you here with your roots t-shirt. If you made a configuration change or added a new library, and if you automatically check some of these metrics, then it should be immediately coming up at the end of the build. When you use Jenkins, run your test, and then the build should scream, you just introduced the n+1 query pattern, or you're making too many more calls to a service that you didn't call before. Okay? So we can automate the architectural checks. We can also automate performance checks. Same with some of the metrics, whether it is CPU, whether it's throughput, whether it's response time, what you guys mentioned in the beginning, or whether it is things like connection pool utilization, whether it is any of the metrics in your infrastructure, we can compare them build to build to build, and then immediately flag it. Now, we got some inspiration, and I really can highly recommend following Acacio Cruz. I met him 2 years ago at a conference, and then he also spoke at Dev1 last year in Linz. I also have a podcast with him, so the Pure Performance Cafe, episode 50, he's actually talking about how internally at Google, so he's managing the SRE team at Google in Zurich, and he was talking about how they treat everything as code, how they automate all these checks, and how they build resiliency into their build environment. So I got a lot of inspiration for what we built in the open source project from him, as well as at Dynatrace itself. We have a performance engineering team, and what they do, they also automated something that they used to do manually. So what they used to do manually, they looked at charts and dashboards like this. So Thomas is actually the lead engineer here. Every night he gets a new build deployed into a system, and then he runs different sets of performance tests, and at the morning when he comes in, he then looked at response time and throughput and all these metrics, and then he basically compared them. And then he said, how does this differ? But he said instead of doing it manually, he just automated that. So he queried the data as the test was finishing. He put them into a database. So for every build now this is now obviously a little report that he wrote, but for every build, he had a column here. For every metric, he had a row, and then he did some very simple regression detection. So he basically said, I want to be notified in case a key metric is getting 1, 2, or 3% higher than the previous build that we marked as good. So this is a very simple visualization with a heat map. So it's just simple regression detection on metrics, right? So that's what he did. And then we took this and we said, well, we can actually make an open source version out of it. And that's what we did. So as part of the Captain project that I'm advocating right now, which is doing CD and CO, so continuous delivery and continuous operations, we have a component that is called Pitometer that is automating, pulling out different metrics from different tools and then grading them and giving us a result. So here's how this looks like. On the left side, we have this Pitometer spec file where you specify where does the data come from. Right now, we support Prometheus, we support Dynatrace, we support Neoload. It's a very fresh open source project, so we're encouraging people to contribute. But you specify where does the data come from and what's the query. When Pitometer later executes, it pulls the data from that data source, right? It then also allows you to specify thresholds, just as Thomas does. There's 2 versions of it, either a static threshold if you have hard-coded limits, or you can also say compare with a certain percentage to the last good build, or just to the last build. But the idea is, if my threshold in this case is 2 gigabytes, I say after the tests, I should not use more than 2 gigabytes of memory or overall, then you can specify a threshold. And what you can also specify, and this is a little hard to see, that's why I use my fancy thing again, you can define a metric score, 20 points. So the idea is, we are grading every single metric, and we give 20 points away in case I am below the threshold. We're getting 0 points away if we're above severe. And in the next example, you also see what happens with warning. So we're getting the data, and then we grade. So assuming if the value after the test is 3 gigabytes, or let's say the max during the test, then it breaches that threshold, so we get 0 points. Looking at the next metric, because this works with multiple metrics from different tools. In this case, I'm looking at conversion rate of Dynatrace, and I also have thresholds. Now I have severe and warning. And in case the value is, let's say, 3.9%, then I get 10 points. Why 10? Because 3.9 is between the gray area of warning and severe. And so our strategy right now was, you get all the points if you are below warning, you get 0 points if you're above severe, and you get half the points that you can make if you are between warning and severe. And then at the end, you can also specify what is your objective. How many points do you need for a build in order to consider green? And in this case, the objective was 30 points. Well, we only have 10 in total. Therefore, this is not a good build. Does this make sense? Yeah, very simple. Open source project, you can extend it. We also extended it as Dynatrace because Dynatrace is one of the data sources. You saw this screenshot earlier. So with Dynatrace, we automatically monitor things like, I have a service and under load, how does, for instance, Kubernetes scale up? Does it launch 2 pods, 4 pods, 400 pods to sustain the load? So I can also say, I want to look at this metric on how many resources I need to sustain a certain load, plus also the incoming and outgoing dependencies. So all the things I told you about earlier can now also be specified in the Bitometer file, where I, for instance, say, my service, when I'm testing it with load later on, my service should only talk to 2 other backend services, this database and the other service. If a new regression, if a new dependency comes in, I immediately want to be notified. So, Bitometer, you can use it standalone, obviously. It's just a set of Node.js libraries. You initialize it, you specify your data sources, you can write your own if you want to pull in data from other tools. It's just a node interface you need to implement. You have to specify which grader you want to use. Our grader right now supports thresholds, static ones, and the ones that compare with the previous build. But you can write your own, and then you just run it. And then at the end, what you get out is a result file, where you get individual values and also violations and a total score. Right? It's a JSON file. Just run it and that's it. And yeah, then the new thing that we just implemented is what I mentioned earlier. You can compare it with the previous build. So this is how you specify upper severe percentage, upper warning percentage. We also support lower severe and lower warning because certain metrics are bad when they go up and some are bad when they go down. For instance, available connections in a pool. And then we also have our first version of a little visual representation. Okay? So you can use this today. Hopefully you find value in it. Hopefully you contribute. And the bigger project where this is part of is called Captain. There's YouTube videos out there where I explain how Captain automates continuous delivery in Kubernetes environments. And one of the components we use in Captain is also Bitometer. So after deploying an artifact in Kubernetes, after running the tests, we run the grader. And if it's good, we automatically deploy it into the next stage or promote it. If it's between warning and good, if it's like kind of not so good, then we actually reach out to Slack channels, for instance, and say, you need to look at this, somebody needs to review, and if it's completely bad, we don't promote it. But yeah, so this is part of this open source project. And because I'm running out of time, I think the last slide that I have, if you want to learn more, these are all the links of the stories from Adrian, from Thomas, and from Acazio. And then the Captain and Bitometer links. And the slides, I'm sure, will be up on SlideShare soon from my side. And I'm sure the conference team will also contribute it. And the only 2 tickets I have left, I'll take from me and my wife tonight. So I think I gave actually all the tickets away. Questions, because I think we still have 2 more minutes. And I will be here, obviously, for a little while longer, but just a couple. Who learned something new today? Here we go. Who didn't learn anything new? Yeah. You just falling asleep. Well, I say thank you.